The student stares blankly at a complex physics equation, sighs heavily, slumps back, and abandons the assignment entirely. Educators are witnessing a severe resilience deficit. It often presents as a lack of motivation, but data suggests a structural collapse of working memory. Students can process the initial steps of a task, but they struggle to maintain the quality of that processing as the complexity builds. We can quantify this breaking point using a concept from queuing theory: time to abandonment. By applying the Erlang-A model, researchers can measure the exact duration a student will tolerate academic friction before exiting the system. Learning management systems provide an objective look at this phenomenon. On rigorous multi-step problem sets, timestamps reveal that students are hitting a cognitive wall and logging out at the 12-minute mark. This happens because we have failed to distinguish cognitive effort from cognitive stamina. Effort is the immediate mental exertion required to decode a problem. Stamina is the capacity to maintain that focus over time, regulating fatigue and distraction during prolonged mental demand. Today's learners have the capacity for effort, but their baseline for stamina is breaking. To find out why, we have to look at the factors that deplete their cognitive battery before they even enter the classroom. Using digital screens to regularly pacify a child's distress establishes a neurodevelopmental baseline optimized for high stimulation, low friction environments. This reliance on digital pacification contradicts the World Health Organization's guidelines, which recommend zero screen time for infants and strictly limited use for toddlers to protect early cognitive trajectories. This digital fatigue is compounded by how children learn to speak at home. In the Philippines, many households adopt an English-only rule to chase global mobility. This well-intentioned shift imposes a massive extraneous load on the student's working memory. Nativist theory suggests that language acquisition is an innate mechanism tied to social interaction. When parents artificially constrain natural household speech with a second language mandate, the depth of a child's linguistic processing can be stunted. When those students are later forced to solve complex physics problems in that second language, they must expend mental energy to coding the syntax. Their working memory reaches its limit twice as fast. This mental depletion often triggers a physical coping mechanism that targets the student's biology directly. During high-stress exam periods, students frequently turn to ultra-processed convenience foods, a diet shaped by the historical Americanization of local foodways. Research shows a dose-response association between this diet and academic failure. Over time, a chronic lack of micronutrients compromises the integrity of the myelin barrier, the fatty insulation required for neural signals to travel efficiently. This biological degradation slows down processing speed, making rigorous tasks feel even more exhausting and accelerating the cycle of cognitive fatigue. A brain wired for rapid algorithms, burdened by a second language, and starved of neuroprotective nutrients, creates a perfect storm that effectively empties the student's cognitive battery. Intellectually exhausted, the student opens a new chatbot window, seeking an immediate, frictionless bypass for their current academic struggle. This leads to AI sycophancy. Large language models have an algorithmic tendency to flatter and validate users, even when logic is flawed. Optimized through human feedback to maximize user satisfaction, the AI is mathematically discouraged from providing the intellectual pushback students actually need. By outsourcing their work to a sycophantic algorithm, students eliminate the final remnants of intellectual friction, causing their independent critical thinking to atrophy from disuse. Cognitive stamina is not a fixed genetic trait. It is a plastic capacity that can be systematically rebuilt through deliberate pedagogical design. The FDG Academic Resilience Framework provides a roadmap. It is a toolkit for educators to deliberately reintroduce the right type of friction into the curriculum. The first pillar is segmented friction. Curricula are broken into modules that progressively demand longer periods of focus, safely expanding a student's cognitive endurance without triggering a total collapse of working memory. Second, by utilizing linguistic scaffolding and removing punitive language policies, instructors allow students to focus their mental energy on scientific concepts rather than vocabulary decoding. Finally, instead of banning AI, institutions can evaluate the interaction using the sycophancy detection quotient, or SDQ. High marks go to students who force the AI out of its agreeable baseline, using the technology to generate rigorous critique and iterative problem solving. To restore scientific grit, we must stop paving over every intellectual hurdle. We must stop treating struggle as a failure, and instead engineer the right friction back into the classroom.